another example that kind of goes from start to finish, from where we've been this whole chapter talking about inference. All of our examples that we've done in class so far have involved this truckload of potatoes and whether they had defects greater than 8% or not. So what I'm going to do is I'm going to pick up another example very similar to this, which I found, and I kind of had to laugh because it involves using drive-through food service, which we have all become too comfortable or too familiar with over the last several weeks. But anyway, we'll walk through that example, but I do want to remind you with a couple of slides of where we've been, and I also want to give you a word of encouragement that I think I may have left out in our previous example or previous discussion. So what I'm going to do, I'm going to pull up the PowerPoint slides that we've been looking at. Let's see. Let me go back a page or two because, okay, so we started this example with perfect potatoes, and we were testing the hypothesis, is the true proportion of potatoes with blemishes equal to 8%, or is it in fact some value greater than 8%? And that's what we talked about, I think, the last 2 days we were together. And we talked about a scenario for type 1 and type 2 error in each of those cases. Type 1 error would be, he concludes that the proportion of blemishes is greater than 0.8 or greater than 8% when it is not. Type 2 error would be concluding that the proportion of blemishes on the truck is less than 8% when in fact it's not. Okay, so that's the type 1 and type 2 error, and we went through these calculations for what does it mean that the significance level is at 5% or with 95% confidence. So we did that calculation, and then we looked at this graph, and we said type 1 error is the probability that when the true proportion is 0.8, that our p-hat value, which we calculated, if that p-hat value is greater than 0.0999, if that p-hat value is greater than this particular value, we're going to land in this type 1 error region, and we would reject the null hypothesis even if we weren't supposed to. Okay, so we did that calculation, and I showed you how to calculate this value of 0.999. Okay, and then we talked about type 2 error. Let me scroll through here a little quickly. We can come back to this if we want. We talked about type 2 error, which is a failure to reject the null hypothesis when it really is in fact false. And the probability of that is called the power of the test. And we went through this discussion. We went through this discussion here where the power of the test is the area to the right of our p value here, 0.099. And we said, okay, the power of the test is 0.75. So we would correctly reject the shipment about 75% of the time. Type 2 error then is the complement of that is 1 minus that. So type 2 error lies here. So I say all that to say this. You will not be required on the test to calculate the power of the significance test. You won't need to be able to do all of this, to do these calculations, which that's good news. What you will be able to do is to be able to, let me say it a different way. What you may be asked to do is to describe what is meant by type 1 and type 2 error. What does it mean in a certain scenario that we have type 1 and type 2 error? And you might be asked to identify the power of the test given a particular value. So I don't want you to spend a lot of time worried about how to do these calculations. What I do want us to do is to go through another example today, and then even look at hopefully this applet that I've dug up will work, and we can kind of experiment with it and see how type 1 and type 2 error interact. Okay, so let me get back to, so let me introduce you to our next example. And this one deals with fast food. Like I said, which I've been to more drive-through windows in the last 2 months or the last month and a half than I ever want to see again. But here's the scenario, and I thought about this example. I don't know if you've waited in line at Ski Daddy's, but the line at Ski Daddy's is particularly long. And oops, we've got a typo here. Let me, I don't know why that. Just bear with me here. Okay. Okay, so we've got a case where a manager at a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait more than 2 minutes once their order is placed. And I guess when you're sitting at fast food, 2 minutes seems like an eternity. So the next time you go to a drive-through window, just look at set your stopwatch and see how long it takes you. So based on his previous records, the proportion of customers who had to wait 2 minutes was 0.63. So based on historical data, the true population of customers who waited more than 2 minutes was 63%, that's a high number. You know, that's almost 2/3 of your customers have to wait 2 minutes to get their food. So the manager wants to improve this and decides, okay, I'm going to dedicate a new employee to work with drive-through orders. And I'm going to try this for a month, and we'll see how it works. So the test that we'll be performing here is a significance test where the null hypothesis is the true proportion of customers who has to wait 63% of the time. Against the alternative, do they have to wait less than 63% or 0.63? And the reason we have picked less than here is we want to improve, or we want to reduce the amount of time they have to wait 2 minutes. So the alternate hypothesis here is we want to see if the population proportion can be less than 0.63, and where the P, the true, is the true proportion of drive-through customers who have to wait more than 10 minutes or 2 minutes. Okay, so P is not how long they have to wait, it's the proportion of customers that have to wait more than 2 minutes. Okay, so I think a really valid question that will come up in a couple of weeks for you guys is, in this context, describe type 1 and type 2 error. Okay, so that's part of it. And the second part will be to explain the consequences of each. Okay, so that one is kind of the interpret question. And again, I think that's fair game for the exam on the 22nd. So type 1 error. What is type 1 error? Well, I found a meme again on Instagram that I want to pop up here. I want to show it to you. Maybe this will help you kind of remember the difference between type 1 and type 2 error. Type 1 error is telling somebody you're pregnant when they can't be. Okay. Type 2 error is telling someone you're not pregnant when they obviously are. Okay. So you've heard me say many times, I'm a visual learner, and I can remember this picture much better than I can remember a string of words. However, if you're a person who likes words, then go back to our dialog boxes of type 1 and type 2 error and just use that. But I can see this in my mind much easier than I can see something else. So type 1 error in this case would be, let's see what that is. Okay, type 1 error would occur if the manager decides that the true proportion has been reduced when it actually hadn't. So at the end of the month, if he concludes, based on his sample, he's going to collect data for the next month, and out of that data, he's going to get a p hat. And if that p hat value causes him to conclude that the proportion of customers who have to wait has really been reduced, has been reduced when it really hasn't been, then that's type 1 error. And the consequence of that is the manager has spent that money to pay the additional employee, and it hasn't improved his circumstance. In other words, the alternate hypothesis, we couldn't conclude in favor of the alternate hypothesis that the proportion of customers who waited a long time has actually gone down. Okay, so type 1 error would be if the manager decides that the true proportion who waited a long time has been reduced, but it really hasn't been. Okay, so we reject the null hypothesis when it in fact is still true. That's type 1 error. We reject that when in fact it is true. And so the consequence is he's paying for an extra employee that really isn't helping him serve his customers better. Okay, so type 2 error would be this, was that the customer said, oh, it really hasn't improved, when it in fact actually had been improved. Okay, so the type 2 error is failing to reject the um, failing to reject the null hypothesis when in fact it's false. And the null hypothesis is false here because it really did go down. It is truly less than 0.63. So the consequence here is that he would say, well, I really don't need that employee, so I'll get rid of them. And because they're not really helping. And now service goes back to where it was before. It had truly improved with the additional employee, but he doesn't recognize it. So he gets rid of the employee, and bad service returns, or slower service returns at the end of all of that. Now, don't panic that you don't have to write all this stuff down. I will send this to you after class. You'll get these. I mean, they'll be on the video, but I will also send these as a PDF to you so that you can read through them and have them as an example. Okay. So let's keep going here and talk about what does it mean when we carry out this test. Let's see what he wants to do. So we were looking at a null hypothesis of the true proportion of customers who wait a long time is 0.63. And we want to test the alternate that the true proportion has been reduced, that it's actually gone down. And so he decides to take a random sample of 250 orders at a significance level of alpha equals 0.1. The significance level is 10% here, okay? An alternate way of saying this is we want 90% confidence. When you say that you want 90% confidence, you're talking about an alpha of 10% or 0.1. So type 1 error means to reject the null hypothesis when it is in fact true. In other words, to reject the null hypothesis, we would find in favor of the alternate, and our conclusion would be that the true proportion has gone down when in fact it hasn't gone down. Okay, so out of this 250 samples, we could get a p hat that is small enough, that is less than 0.63, that would allow us to make that type 1 error and conclude that it has really gone down. And what the significance level means is that this will happen in about 10% of the samples that he could take. So out of all of the orders that came through his drive-through during the month, when he randomly selects 250 of them, about 10% of those samples would have a p hat low enough that he would conclude in favor of the alternate hypothesis, when in fact the true value is still at 0.63. That's what type 1 error means. And so in the diagram, this is what we're looking at. Okay, so type 1 error is the true proportion remains at 0.63, but the p hat that he collects based on his 250 random samples lands in this area here. Because this is a left-hand tail test, since it is P is less than some value. If P hat lands in this blue shaded region, we would reject the null hypothesis, when in fact the null hypothesis is still true, when in fact the true proportion of customers who have to wait a long time is still 0.63. So this is type 1 error. Now you can see the importance of thinking about choosing what this type 1 error level should be. I mean, you don't want this to happen very often. So you might say, well, Barry, why don't I just always pick alpha to be a really, really low number? Well, let me answer that question with the next slide. So let's talk about the power and significance of these tests. If we always want to have we want to reduce the value of type 1 error. We want to reduce the probability of type 1 error. So you could say, I always want to do a 99% confidence level test, which would have an alpha of 1%. Well, what's the drawback to that? Everything is kind of in balance here in statistics. You can get 99% confidence, but it's going to cost you something. And that cost is how many samples do we really, really have to take? And so here's what I want us to talk about, okay? So if you insist on a smaller significance level, such as 1% rather than 5%, or 10% in the case of the restaurant owner, you have to take a larger sample. A smaller significance level requires stronger evidence to reject the null hypothesis. And that makes sense. If we want to be more certain that we're not going to draw a false conclusion, then we have to take more samples. And so the difficulty is it may cost me more to take more samples, or it may take longer, or I may not be able to take that many samples. Perhaps the number of samples required to get to a 1% significance level is so many that I practically can't get it done. So in the type 1 error, smaller significance means a larger sample. Keep that in the back of your mind. You'll need to be able to reason through that. On the other hand, what is the power against committing type 2 error? So let's say that you want 99% level power rather than 90%. Again, you have to take a larger sample. Higher power gives you a better chance of detecting a difference when it's really there. And the way I look at that, you've been in biology enough to think about the power of a microscope. And in most microscopes, you can adjust the amount that you can zoom in on your slide, and that's called the power of the microscope. So to see a really, really small element on the slide, you have to go to a higher power. Well, that's what happens here. To be able to detect a difference between your null and alternate hypothesis, you have to use a higher power, which again requires a larger sample. And the question is, do you have the resources to conduct the test with more samples? That's really the question. That's really the issue here. So the conclusion we want to make here is that any significance level and any desired power. Significance level is refers to type 1 error. Desired power refers to type 2 error. Detecting a small difference requires a larger sample. Okay, so anytime we want smaller significance or higher power, which is really in an ideal world, that's what you would want. In an ideal world, you would conduct all of your tests at 1% significance or 99% power, and you'd be done with it. You would be very, very, very confident that you're not going to make either type 1 or type 2 error. But in the real world, in a practical matter, taking more samples costs something. It takes more time. It costs more money. It involves, think back to Gallup surveys. It means making more phone calls, making sure that we get more people to answer the phone and take our survey or participate in our survey. So another way of looking at it is smaller significance or higher power just requires more resources. So in the real world, we have this balance between I want to reduce the chance of making type 1 or type 2 error against the practicality of how many samples can I really take. So the store owner might say, man, digging through my records to to find 250 samples, that's really hard. That's really time consuming. What's the difference if I just stop at 100? What happens to my significance level and my power if I just stop at 100? And that's where we're gonna go next. Okay. So let's presume that the store owner decides, okay, I need, in order to be sure that this additional cost for the additional employee is worth it, I need the percentage or proportion of customers who wait more than 2 minutes to go down to 0.53. In other words, what he's making a trade-off here is that the additional cost of hiring another person is offset by the additional revenue generated because fewer people have to wait more than 10 minutes. So he wants to test, okay, what is the cost associated? What happens if I do that? And oh, by the way, instead of taking a random sample of 250, I'm going to just take a random sample of 100 because I'm really in a hurry to know whether I can't wait a whole nother month to find out, is this valid? Okay, so here's what we've assumed so far. Our null hypothesis is the true proportion of people who wait more than 10 minutes is 0.63. Our significance level has been 0.1. The number of samples we took is 250. And now I'm trying to determine if after I make the change by adding the new employee, is the true proportion down to 0.53. Okay. And so what we're going to do is you've seen these, we've used these applets in class a little bit later. Again, I'll send you this link and you can toy around this somewhat. Now, what you'll see on this applet is the hypothesized value P will be represented by the Greek letter pi. And the reason for that is sometimes textbooks use pi to represent the true proportion p. And it's kind of funny. I learned why that is in talking with Romano, because if we were Greek, if we were speaking Greek right now, when I pronounce this letter, it would sound like P. I wouldn't pronounce it pi in Greek. I would look at this letter and call it P. And so in many courses, in many textbooks, the Greek letter that we call pi is synonymous with the English character we call P. So these two things are the same. So when you see the Greek letter pi, just think of P. Okay, so I'm going to try to split my screen here and pull up. Oops, yeah, this is what I want. I want this guy here. Okay, so I'll send you the link to this page, and you're gonna. It's kind of funny. The title of the applet is called "Improved Batting Averages." Okay, so you're going to click on that, and it will look like this. So now I need to split this guy. And I need to bring this guy back up so that we can see these side by side. It's a little hard to see, but we'll just have to do the best we can. Okay, so the hypothesized value now, we want to put in 0.63. 0.63. The alternate hypothesis we want to test is 0.53. The sample size, oops, I've got a typo. Okay, Mr. Applet. 0.53. Okay, the sample size we want to put in is 250. We want 250. And we want to see a large number of samples.
I thought we were doing 100.
We're going to do 100 next. We're going to see.
Okay.
We're going to see what the. Oh my gosh! When I don't see your faces on my screen, it scares me when you talk up.
Sorry.
Oh, it's fine. It's fine. I'm going to. The reason I'm going to do this one is so that we can see the difference between choosing a smaller sample size. We're going to see what happens to our graph when we choose a smaller sample size. Okay. Okay. So we're going to draw samples, which is right here. Okay. So really fast, we just did 10,000 samples of this test where the true proportion is 0.63. And sure enough, I mean, we look at the middle, the tall peak here is right at 0.63. The alternate was at 0.53. And so this is, this is really all we need to see here. Okay. Okay. So now that we've got this, we want to begin to understand type 1 and type 2 error. Okay. So we want to choose the level of significance. Choose one level of significance. That's it. and we want alpha to be 0.1. And so we'll take a count of how many times that actually occurred. Okay, so what just now happened? All right, so what happened is out of the 10,000 samples, we counted how many of them would be cut off, how many of them make up a 10%, how much of the area is 10% here. And there were 925 of them. 925 out of the 10,000 fell into this range here. So out of 10,000 samples, we had a p hat less than 0.588. I think that's 0.588. Okay. And so that p hat of 0.588 is where we would say, oops, if we get a p hat in this range, we're going to reject the null hypothesis when in fact it's true and conclude in favor of the alternate, and when that's not true. Okay. And then verify that the power of the test when p is about let's see, I forgot where that is. Let me. So now what we want to do is we want to change alpha to 0.01. 0.01. And we'll do a recount, or kind of keep this picture in your mind and see what happens. Okay, so alpha went way, way down. Only 77 of the samples had a p hat low enough that would fit in this region. And this region here accounts for 1% of the area. Okay. And so we would say, well, heck, why don't we just go for 1% all the time? Well, what that means is we have to see. Hold on, let me expand this for just a minute. Okay. Up here, notice how the power of the test has gone down. Let me put this back to 10%. And notice up here, the power of the test is right here. Okay. And so when this changes, notice what happens here. We have to work much, much harder to get to where we want to be. Okay. So now what we want to do is, let's say we want to change the alternate value to be 0.5. We want to make it even lower, not changing anything else. We'll choose level of significance, and we'll put alpha back to 10%. Now, whoops, got to draw our samples. Sorry. Okay. And notice what happens again. we still have roughly the same number that fall in this 10% area. And if I change alpha to 0.01, then it shrinks down again. Notice what value a p hat has to become. If I get a p hat less than this value, I will conclude that the null hypothesis is true when in fact I'm sorry, I will reject it when in fact it's still true. Notice that this shape, the mean of my population still hasn't changed. I haven't done anything to change that value. Okay. So now let's see what happens when I change the sample size to 100. I take fewer samples. Okay, now look what happens. My shape is roughly the same, but now look what happens. Only 90 of the 10,000 samples showed up. And so when I take fewer samples, I get fewer opportunities there are fewer tests in this region. And so I am more likely to get one of those values, okay? If I look at the, there's what I'm looking for. Okay, so the power of the test now has changed. Let's go back and look at these. Let's go back. Let me put this back to 250. All samples. And now I want to count. Okay, so with 250, the probability of committing type 2 error is really, really, really small. Okay, but when I take fewer samples, that power gets it gets I'm even more likely to commit that mistake. Okay, so there's just a balance between the number of samples and the significance level and the power of the test that we want to conduct. Okay, and so what I'm going to ask you to do is just spend some time looking. I'm going to give you an example problem to work on when we're done here, and tinker around with this. Excuse me, my dog Dixie is begging for attention. Dixie, come here. Come here, girl. Play around with this applet, and you can see how changing these values helps to, you can kind of visualize what's going on here, okay? Let's see, so let me get back to here. Okay, so it's just us again. All right, so here's what we need to do. First of all, I want you I'll send you an example to work on here after we're done. Use this, I'll send you the link. I'll send you these slides. You can use them as notes. tomorrow, I'm going to be helping out. Our church is doing a service project, and I won't be done at 1 o'clock. So what I'd like to do is postpone this. I think I'll be done by 2. But my question is, what if I'm not done till 3? We all still be available? Give me a thumbs up or something. Yeah, you'll be available at 3. I'm certain I'll be back home by 3 and we can get back together. We'll talk more about this example. And I will also want to talk to you about whether you've had to take the chance to take the demo exam. You should have yesterday received an email from AP, from the College Board, that gives you a link to take the demo exam. If you haven't done that, I want you to do that between today and tomorrow. It shouldn't take long to do all of that. And I'll walk you through. If you have any questions, I'll try to help you get through those. But the key thing is I want to make sure, A, that you did receive your link, and B, that you can make it work on whatever device you plan to test with, whether you're going to test on your phone or your laptop or a tablet of some sort. If you can make the demo work on that device, then you should be fine wherever you are. If you have limited internet and you try it at home and it works fine, then that's good news. If you try it at home and you have trouble, then we need to identify that ahead of time. And the demo will work for, it will give you feedback for all of your tests. In other words, if you're taking chemistry and AP Lit and stats and I don't know what else, world history, I don't know. If you're taking those tests and the demo works, you're able to upload, type in your responses and upload them, then you're fine. You're good to go. If you have trouble with that, then we need to identify that right away quick so that we can get some help. Okay? All right. So before we get off, any questions about anything? End of school, AP exam, what we just talked about? I will say this, that most days from now on after we meet, I will still probably assign, or I still plan to assign you some work. But from now on, it will be ungraded. You don't have to turn it in to me anymore. If you want to turn it in so that I can look over it, then go ahead and do it. But my plan will be every day when we get together, I'll ask you, hey, did anybody have questions about yesterday's assignment? I haven't been doing that because several students can't stay day to day with us because of work schedule or internet or whatever. And so I haven't been talking about answers to questions in class to give those other students an opportunity to work through them without any advantages, without the advantage of knowing what the solution is. So, but now, since I'm not grading anything, I'm not really worried about that advantage. So it's really up to you as to how hard you work on the things that I assign you. What that means, though, is the way I look at it, the more elbow grease you put in now, the better off you'll be on test day. Now, it's up to you. It's up to you how you approach it. Okay, so I'll be here to help you in any way I can. My advice, give it a shot. If after a reasonable amount of time you're still struggling, wait till class tomorrow and we'll talk about it. Okay? All right. So let's, unless there are any more questions, we'll sign off and I'll see you tomorrow at 3. I'll post the change of time. Now it should be only for Wednesday, Thursday and Friday. I expect to be available at 1 o'clock both days, but tomorrow is the only conflict I have. So we'll try it at 3. All right, gang. Unless there are any other questions, I'll see you tomorrow. Have a great one.